Greetings, friends of chemistry. I'm here doing the second edition Apologia. I'm in Module 2, and I'm looking at Module 2 on your own 2.6. 2.6 is found on page 53. I'll also do 2.7 in this video. Okay, so 2.6, first I'm going to read the problem, then I'm going to go back and do a little explanation of how to solve it. A 502 gram iron rod is heated to an unknown initial temperature. If, while cooling down to a temperature of 22 degrees Celsius, the rod releases 597.5 joules of energy, what was its initial temperature? Hint: when an object loses energy, its Q is negative. We will discuss this fact in detail shortly. Okay, so earlier on page 49, we were given a discussion about measuring heat, and we were given equation 2.3. Equation 2.3 says Q equals M times C times delta T. Okay, so Q is the amount of heat absorbed or released, and it can be positive or negative depending on whether heat is absorbed or released, right? M is the mass of the object we're talking about. C is the specific heat. So you'll either be told that, or you'll calculate that, or you'll look in a table or something like that. And delta T we find by taking the initial temperature and subtracting the final temperature. So T initial minus T final. That can be written T I minus T F. Okay? So that's how we solve for delta T. Okay. So the variable C there, that specific heat, we discussed in the previous video on your own 2.4 and 2.5. The specific heat is the amount of heat necessary to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay, so I'm going to erase all this. Well, I'm going to erase some of this. This formula is pretty important, so I'm going to leave it up for now. So this is going to have to help us in 2.6. Okay, so we have a 502 gram iron rod. That's our mass, right? We don't know the unknown initial temperature, okay? We know the final temperature. Okay, and we know how much energy is released. That's 597.5 joules. Okay, so, and that's the Q, sorry. Now we're talking about iron, so we're going to look at the table 2.1. Table 2.1 says that the specific heat of iron, the C, is 0.4521 joules per gram degrees Celsius. Sorry about that. Okay, so now we can go about setting up our equation. We don't know the delta T. This is what we don't know. So we're going to use algebra now to make this equation look like what we want. We're going to say delta T equals Q divided by M times C. All right, so now we're going to plug in, and I'll come back to this later when we are ready to solve for delta T. So delta T is going to be equal to, okay, so this is going to be a negative Q, all right? Why do I say it's going to be a negative Q? because it's released 597.5 joules of energy, all right? So is negative 597.5 joules per gram degrees Celsius, that's Q, over the mass, 502 grams, times the C. Excuse me, this is a lie, bad teacher. This is just joules, I beg your pardon. This is just joules. And the C is 0.4521 joules per gram degrees Celsius. Sorry, this is just the energy. Okay, so using our math skills, get rid of those units. We're going to end up with something in degrees Celsius. And I'm going to allow you a moment to use your calculators while I run and grab mine. I've performed this equation already. I'll be honest and tell you I pretty much do all of these problems before I record the video for them. So I'm going to say 597.5 divided by 502 times, now see, this isn't going to work. Let's do 502 times 0.4521 is, this calculator isn't a very good one. And now I'm going to divide 7.5 divided by 226.9542. This calculator won't let me use parentheses. So since I couldn't use parentheses to multiply my denominator before I divided the numerator, I multiplied these and wrote down that answer, and then I'm dividing the numerator by that answer. So the answer I get is negative, the delta T is negative 2, comes out to 2.63268. All right, so how many significant figures can I use? Let's look back at our original equations, or our original numbers. This one has 3, this one has 4, this one has 4, so we're limited to 3. So we want 3, so this is a 2, so it's negative 2.63 degrees Celsius, okay? So now we're going to go back to what I erased, which was delta T equals the initial temperature minus the final temperature. We are told the final temperature, so we need to find the initial temperature. So we're going to say Ti is going to equal delta T plus oops, I'm lying. I'm lying again. This is so bad. How bad? So bad. This is the final minus the initial. So sorry. I apologize. The delta T is the final minus the initial. I read it wrong in the book, but I have it right here. Really, I do. See? I need new glasses. That's my problem. All right, so the initial temperature is going to be delta T plus the final temperature. All right, so the delta T, no, what am I doing here? Let's solve this again. Okay, so okay, now I'm going to make all these positive, negative, so I say temperature final minus delta temperature equals initial temperature. So that is 22 degrees Celsius, we're told in the book. moment. We're told that the final temperature is 22 degrees Celsius minus negative 2.63 degrees Celsius. We're going to add that basically. That gives us 24.63 degrees Celsius positive. But since we're adding here, okay, we have precision to the ones place and precision to the hundredths place. So we can only be precise to the ones place. Can you see all this problem? Ooh, there we go. So since we can only be precise to the ones place, the answer we're going to report is 25 degrees Celsius. So the initial temperature is 25 degrees Celsius. Okay. So I hope that was helpful and not too confusing. Sorry about that confusion on my own part about the delta T. Now I'm going to do 2.7. 2.7 says, if a 15.6 gram object requires 836.8 joules of heat to raise its temperature by 21 degrees Celsius, what is the specific heat of the object? This is a fun one. Okay, so to solve for Q, Q is the mass times the specific heat times the delta T. So we are told Q, we are told M, we are told delta T. What we do not know is C. So we have to solve for C. So we're going to use algebra. C is Q divided by M times delta T. All right. Now we just plug in our numbers and do the math. There's going to be Q is 836.8 joules, right? The mass was 15.6 grams, and the delta T is 21 degrees centigrade. Okay. So again, we perform the math, and with my limited calculator, I'm going to do the denominator first. 15.6 times 21 gives me 327.6 grams degrees Celsius. Now I'm going to divide 836.8 divided by 327.6. That will give me 2.5543, and it's joules per gram degrees Celsius. Okay, whoops, let's see. So, looking at my original numbers, I am doing multiplication and division, and so I need to be consistent with my significant figures. This one has 2, this one has 3, this one has 4. I need to have only 2 significant figures in my answer. So this 2.554, et cetera, I'm going to round to 2.6. C is 2.6 joules per gram degree Celsius. Okay, and that's it for 2.7. Again, if you have any questions, give me a call or send me an email.